and we'll start with Dr. Neill, who's talking about tracing source areas of hydrological hazards to optimize spatially targeted mitigation, a multi-agent approach.
Okay, thank you. So I'm also going to touch on use of agent-based models, but here in quite a different context. So the hazards that I'm interested in relate to flooding and issues of water quality. Now, historically, these have both been managed using point-based approaches. So for floods, that's tended to be implementation of structural defences, particularly in response to given events. Whilst for water quality, it's meant to focus on point sources of pollution. Now, it's increasingly recognised that we need to sort of move away from these approaches and also think about nature-based solutions, for instance, reforestation and increasing storage of water within the landscape. Now, by working with natural processes, these solutions offer greater resilience to environmental change and the types of hazards people might be faced with. And they can also offer multiple benefits, both with respect to managing several hazards simultaneously, but also increasing biodiversity and ecosystem services. Now, in order to make sure our nature-based solutions are effective, we need to make sure they are optimally located within our catchment environments. So how do we do that? Well, for floods and water quality, we can think about critical source areas. So these are parts of the landscape where there is a source of floodwater or pollutant and a high likelihood that that source becomes connected to a point of impact. Now, we have several methods available to us for source identification, each with its own resource cost, scale of application, and degree of physical realism. They are meant to be triangles on there. So at one end of the spectrum, we have models requiring minimal information. So these have a low resource cost and are useful for sort of a rapid assessment at larger scales using some form of static average condition. At the other end, we have field assessments. So these are useful for verifying model predictions and trialing mitigation measures, but they are associated with high resource cost, and so their sort of applicability is only at quite small scales. Now, I'm interested in process-based models, and these offer a convenient middle ground between the two other approaches, and we can use them to do dynamic simulations, so we can see how sources of hazards might change over time, and we can look at doing scenario analysis. Now, most process-based models are aggregative in nature, so what that means is we have our catchment and we spatially discretize it in some way, such as through a grid of cells. And we route our water or contaminant cell to cell until we reach a point of impact. Now, for each cell, the incoming flux is aggregated with what's already in storage before the outgoing flux is generated. So this leads to a limitation in that by the time we reach our point of impact, much of the information regarding the spatial origin of our water or contaminant has been lost. So we don't know, for instance, how much came from the blue cell or the green cell. And this is a problem if we're thinking about spatial targeting of mitigation. Now, agent-based models can help us overcome this. They consist of three components. We have our agents, and this could represent a parcel of water or quantity of contaminant. And the agent has a set of characteristics, and it can remember how those characteristics change over time. We then have our simulation environment and a set of rules that governs how our agents behave in response to environmental conditions. Now, in this way, agent-based models offer a process-based framework to gain insight into the spatial origins of water and contaminants reaching our point of impact. And that's because our agents can remember where they entered the simulation and the pathways that they subsequently followed. We also have the flexibility to define multiple types of agents within one simulation, so this gives us scope to consider how we might manage several hazards simultaneously. So my previous work has developed the model for the agent-based simulation of fecal indicator organisms, so this was for use with impaired microbial water quality, and my work in IHRR will use this as a basis for the development of a multi-agent toolkit, which is currently named MACA. And this will be able to offer insight into the spatial origins of the various hydrological hazards listed here. So the initial work I'll do will focus on MACA flood and MACA nutrient. MACA flood will build on work using the minimal information model, requirement model, SciMap flood, which has been applied to the East Rapti catchment in Nepal, whilst MACA nutrient will be developed with colleagues in Costa Rica. Now here, nitrate pollution is a priority issue, and this is a consequence of increasing urban expansion and the use of unregulated septic tanks and on-site sanitation units. But it's also through use of large degrees of inorganic fertilizer on coffee plantations and also intense rainfall that can wash that off the landscape. So there we'll look at doing some source attribution work. So I look forward to hopefully being able to tell you how these projects progress over the coming years. Once we've done the initial development and testing of MACA, we will look to widen participation in its use and further refinement through engaging with stakeholders, seeing what they would like to use the toolkit for and what features they would like it to have. And this will be the first step in MACA being a fully fledged decision support tool, packaged in a way informed by stakeholder discussions. And it's in this way that MACA has potential to help those communities at risk of flooding or impaired water quality through supporting use of resilient nature-based mitigation. Thank you.